Okay, thank you very much. Thanks for coming in such large numbers. Well, it's the start of the presentation. We'll see. We'll count at the end if everybody stayed or not, maybe. Yes, I'm perfectly fine with talking to just few people. If you're really interested, that's okay with me. Let me be the artist who plays in front of just a few people, but gives it all, yes. Okay, huh? Yes, you're the geeks, that's true, yes. You have to be a geek to follow me along the radical object orientation yesterday, and now today it's, well, architectural patterns. But today we are also joined by Priya and Arjun, who are our co-hosts, so to speak. They'll appear on the slides, and one you'll see is the rookie, and the other one is the wise teacher, of course. Yes. So what does it all mean? At first, well, I did that yesterday too, but there's one or two people who haven't seen it, so let me quickly introduce myself because nobody of you has heard of me before. Very, very likely I'm an obscure speaker from an obscure continent, Europe, and who has focused on, well, just 100 million people speaking German. Not done so much in the English-speaking world. So I was focused there and was very happy. But then I wanted to go beyond that, and now I'm in India. Let me start with a quick couple of facts about myself. I was an editor-in-chief of a Visual Basic magazine for a couple of years. That was the beginning of my solopreneur career after being a CEO of small software companies. Then I moved up from writing and reviewing articles to writing books. One even was a bestseller in Germany, which meant like 10,000 copies sold. Great, yes. And did some books in self-publishing, all in German, sorry, not for you. And then I moved on, not true, no, I didn't move on, but I had a short stint with Bill Gates on a stage and made him sweat, yes. Very hard questions I asked him. Yes, he had to think a real lot. And then until he got bailed out by the Microsoft CEO of Germany, who said, "Nee, but Bill, step down. This is too hard for you." I'm doing, yes, I like to do presentations on stage, larger or smaller audiences. I don't care as long as people are really enthusiastic about the topic. And well, as I told yesterday, we have moved to Bulgaria, this small dot here where there's just like 6 million people living in the whole country. The half of Bengaluru's population. It's crazy. You hardly see anybody. I mean, I'm stepping out of the door and immediately I get swamped by people, like so many people. And there, when I step out of my door, I don't see anybody. Like for a whole day, it's just dogs, maybe, or sheep, or cows passing by, but people hardly, if I want to. So this is a lovely place, and of course, as I said yesterday, yes, I'm here for the main reason to follow up with my crush on an Indian girl when I was like about 15, 16 years old. Never meant to be, but still I'm here and I'm glad. Thank you for inviting me. So on to our topic. There's Arjun scratching his head because on LinkedIn he saw a couple of posts along this way here. It's hard to read, I'm sorry. It's about the hexagonal architecture. Someone saying how great that is and it's still helping him in his day-to-day software development business. Yeah, hexagonal, go hexagonal, that's great. Alistair Cockburn invented it in, what, 2004 or 5. So good. And then the other guy says, no, it's not hexagonal anymore. It's clean architecture. Yeah, go with this. You have to structure your software according to that. Then it's gonna break through. It's so easy to maintain. And Arjun is saying, what? I mean, what is this all about? Why do I have to care? I mean, this is stuff from 2005 and 2012 maybe. What happened before that? And is anything happening after that? Has anything happened worthwhile noting after that? Should I stick with architectural patterns from 20 years ago? And well, Priya says, no, I mean, check it out. There's a whole history of patterns, and maybe, just maybe it's worthwhile knowing a little bit more about the history, about what came before and what maybe even came after, so you get an idea this is still in an evolving field, and even in the age of AI, we might want to know about how to structure software. So there have been papers written in the 60s, then something happened in the 70s, it was a little bit quiet in the 80s, and then things exploded from the 90s on, and we are here now. You haven't seen those pictures yet, I guess. You have, of course, seen that from by Robert C. Martin, but what came after that? Something happened. Let's see. The first thing I want to do for you is I want to group those architectural patterns into 3 categories. I think there are categories, and it's good to know them in order to be not so, I don't know, so hypnotized by buzzwords, like the buzzword of clean architecture. Yes, okay, you have to do that. Yeah, but why? What's so special about it? Why was it clean architecture in 2012 and not layered architectures anymore? What is it about it that made it more attractive? So why the change? What happened? So let me group that into certain categories, each titled with a principle. This is the separation of concerns principle, this is the dependency inversion principle, and this is the integration operation segregation principle. So there are principles underlying those architectural patterns. Okay. What is it all about? Why do we have to care about, well, architecture in the first place? Can't we just like code along, code away, yeah, get some stuff rolling? And the answer is, well, Priya says, look at your program. We take a sample program here. The overall scenario is the same as yesterday. There are a couple of flow times or cycle times, whatever. Cycle times is a better word for you, I guess. Cycle times, how long people took to realize an issue, right? Some issues took 1 day, some 3 days, some 4 days. So there's, well, a lot of events happening in your team. All those issues get realized. This list goes into a program, and the program spits out a very, 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 very simple graph, a histogram of the distribution of those flow times. So flow time or cycle time 1, 25% of all cycle times, 2 is 50%, and 5 is also 25%. A very simple histogram, not very graphic, but well, you get it. Okay, a program is doing that, reading from a resource here and writing to another resource to the console. That's the scenario for the talk with different implementations. Okay, let's look at this. So Priya says, in the beginning, there was just logic. Logic is this stuff here. Logic is the stuff in software which actually creates behavior. And it's usually inputting data. Data is put into this stuff and it's transformed and it's output. IPO, input, processing, output. That's what logic does, right? Logic is the stuff from somebody, it's not your stuff, and you compose it into a functioning whole. Great. So this is all the code actually doing what the small diagram showed. It's reading from this file and printing a diagram like that. Okay, so in the beginning, like maybe 1950s, 1960s, if you were programming back then, you would be writing just logic and things would be fine. That's the, I would say, the origin of the term programmer, to be able to come up with this kind of solutions. Good. Okay, so this is an image of logic to its extreme. Do you know this language here? It's a programming language. It's Turing complete. You can like write any program in this language. Ever seen that? It's called brainfuck for a reason. So every statement, every single operator is just one letter. Here the plus means incrementing a part of memory, then this is a loop, and there's advancing a pointer in that memory, increasing some other memory location, and so on. And what's the effect? Try to guess the effect. This is print out. The dot means print out the current location's value. What's the effect of this? You know that? You can see that? Yeah, take a picture, throw it at ChatGPT, let it analyze it. This is printing Hello World. Who would have thought, right? It works. It actually works. You take this code, go to an online compiler or interpreter, get it to run, and it says Hello World down here. It's very, very, very few statements or operators, whatever you want to call it. It's called brainfuck. Yeah. You show that to some newbie. This is going to be what you do all your life long, program. They'll turn away, I guess. Okay, fortunately now there's AI and other languages, so we don't have to do that anymore. But it makes very, very clear what logic is. Nothing more than that. Okay, this is creating behavior, and we don't need more for software. So why in the world is there more in your programming languages? Just tell me. Why is there more than logic? Huh? Is that for the customer? The customer needs more than logic? No, it's just for you. It's just for you to be able to manage a growing amount of logic. Okay, so logic creates behavior. That's what we want to see. We want to press a button, input some data, and then press the button and see a result. Maybe that result shows up in a file, or maybe it shows up on your screen, or maybe you don't want to input data by hand, but just move a joystick around, whatever. So it's input transformed into some form of output. That's called behavior, and logic cannot be reduced. Once you're at the logic part of your code, that's it. That's creating the behavior. Maybe there are different ways of creating the same behavior. That's where elegance comes in. You have heard about elegant programming, right? So this like one line of code doing it all. Wow, how great is that? Nobody understands it, but it does it. Wow, that's elegant, right? Like the elegant formula, E equals mc squared. How elegant is that? Yes. In software development, I would argue elegance is not the goal, right? Because elegance is cryptic. So there are different ways to code more or less elegant or more or less clean. But in the end, logic cannot be reduced. Whenever you take away something from logic, the behavior changes. That's what I mainly mean by irreducibility. You cannot take away or move it around and expect things don't change for the user. No. Okay. And logic is hard to understand. This code here in the background, that's the first piece of logic I showed you, to create from the file content this small graph. That is hard for you to understand, but if I give you like 15 minutes, you'll manage. The logic I showed you in brainfuck, that is really hard to understand. To make a point, logic is hard to understand. You have to simulate it in your head. You have to step through it and simulate what's happening to memory, what's happening to resources, and what's going on in this loop. And you have to do that in your head. It's really hard. So what you are really thankful for are meaningful identifiers sprinkled across your logic to give you like paragraphs. Okay, so up to here, this is the result, and it has a meaningful name. Then another 10 lines. Okay, this is the result of another 10 lines. That kind of name. So meaningful identifiers make it kind of better to understand, but it's still hard. But that's where we all start. And logic is, well, needs to be tested, and it's hard to be tested just on its own. The bigger it gets, the harder it is to test, like just the piece in the middle. How do you do that? Just the piece in the middle. Maybe it's a very complicated formula. you came up with like in a dream. And mostly it works, but does it work all the time? How do you, like, do you have a mathematical proof for that? Probably not, so you have tests. But how do you apply the tests exactly to that part in your code? Now that's hard, right? So we need to do better. This is okay for programs in the 50s and 60s with a couple of hundred lines of code maybe, but doesn't scale. Okay, enter functions. This is, let me make a footnote, this is not true. Functions weren't invented to structure code, but that's the story I'm telling. They were invented to save memory. But nowadays, we don't care about memory at all anymore, so we use functions to encapsulate logic, right? So we put logic inside a function and give the whole logic, the whole 10 lines, the whole 50 lines, the whole 5,000 lines. We give it a catchy name and like put it away. Okay, just remember the name and we don't need to look at it anymore. We do that up here, we do it up here, and then, well, there's a whole bunch of logic still outside of functions, but you get it. You get the idea. So functions are here to structure code into units we can better understand because we give these bunches, these clusters of logic a meaningful name. That's great. Good. Okay. Is that all? Enter functions, right? Functions are great. They abstract from the details of the logic. Imagine the brainfuck code, brainfuck logic, and I just gave it the name print hello world and stuff away all the details, the pluses and dots and whatever. That would be great. So functions compose from logic, higher level functionality. They name the logic, so I don't have to simulate it all the time in my head, but just look at the name and know what's going on. Plus, well, they bring convenience and use. Whenever I have a function, I can use all the logic by just calling the function. So think even reuse. Once you come up with great logic, put it in a function, put it on the side, and remember the name and call it whenever you like. Great. Reuse. That's what the object-oriented guys always wanted, reuse. But it was there before object orientation, even mainstream object orientation. And then, well, functions are the handles to grab when testing. That's where you can attach tests to. Call a function with some sample data, know what you expect as a result, compare the result to the actual results or expected results, and see if that matches. Great, that's automated tests. With functions, you can split up your logic into different parts, and each part can be tested separately. That was the point I wanted to make yesterday with the integration operation segregation principle, radical object orientation, to push down all logic into the leaf functions of your call tree. Great, functions. Remember Arjun asked, why do we need architecture, right? Isn't it enough to have logic? No, it's not enough, doesn't scale. Is it not enough to have functions? Well, yeah, it's a step in the right direction, but it's not enough either because, well, instead of 1 million lines of logic code, you might have 100,000 functions. That's still a lot, hard to manage. So enter, now we are onto some theory here, enter modules. Okay. In the 60s and 70s, people still thought a lot about modules. What's a module? There's Boom, there's Parnas, and there's Dijkstra, some important figures back then. And they came up with the idea, okay, let's even more order our code and pack it up into, well, some say components, and the original term was modules. Okay, so it's like building blocks. That sounded like a good idea for different reasons. What does a module do? See, we know what a function is. It packages up, well, it composes functionality from smaller parts. maybe from logic or maybe from other functions. And the module now is not a container of logic directly, but indirectly by packaging up functions. A module draws a boundary around a couple of functions and makes them accessible. Okay, great, thanks. Makes them accessible through an interface. Some functions are published, visible from the outside, and some functions are not. So a module, again, is an abstraction in that it's hiding details. Functions are hiding the details of logic, or in general of composition, and modules are hiding the details of, well, what makes up this topic in terms of functions. It aggregates. So all those functions have something in common, but not all of them are visible. Maybe those functions exist today and tomorrow not anymore. Who knows? I don't care. As a user of the functions of that module, I don't care about the private functions, about the hidden implementation details. And along with the functions goes also state. You know, classes. Classes are a form of modules. There's a whole bunch of module types. I'm not going to go into that. There's a whole module hierarchy. And so we better be clear about our terminology and not mix up modules with components. Because what is the difference between a module and a component? A module is a category name. A component is one type. A component is one type of module. But I don't want to go into that detail. I just want to talk about modules in general as boundaries or parentheses around functions. So modules aggregate functions. So they increase productivity because now we have a larger block of reusable stuff logic. Very handy with the interface. Those couple of functions belong, well, tackled the same topic. Maybe it's open, close, read, write. Oh yes, this is some resource access maybe. Good, pack them together into a module, or encrypt and decrypt. Oh yes, pack them together as a security module or an encryption module, whatever. So modules abstract by hiding details, but it's a different form of abstraction than functions do. Functions compose and modules aggregate. Then modules bring order. You know where you have like apply modularity thinking in your everyday life? I'm sure you do that, and you hate it when certain people don't do that. Your children. You go into the room of your children and you find stuff lying around, like some socks over there and there and there, and some, I don't know, t-shirt over here and there, and a shoe and another shoe. So you hate it, and you say, well, I gave you a wardrobe. Put it in the drawers, right? There's a drawer for your socks and a drawer or a part where you put your shoes and the hangers for your clothes. So that's order. That's what modules do. They bring order to chaos. They give a place to put stuff that's related. All socks are related, even though some are longer or shorter or have different colors. But the purpose of all socks is roughly the same. Don't strangle people with them, but put them on your feet. Modules bring order, and, well, I'm too fast here. And so this is the next slide. Why am I doing this? Okay. And this is expressed in one of the first principles from, I don't know, beginning of the 70s, formulated by Parnas, and the separation of concerns. Separation of concerns means if you are concerned with something in your software, what could that be? You could be concerned with resource access, right? You could be concerned with, oh, how am I going to display the data? You could be concerned with performance. You could be concerned with security. You could be concerned with scaling. You could be with all sorts of stuff in a hierarchical manner you can be concerned with. Within user interface, you can be concerned with inputting data. How do we input the data? Do we set up a form, or do we go with a dialogue, like an AI dialogue nowadays? And how do we output the data? Just a table or graphics? So different concerns within the bigger concern of user interface. That's related to this same responsibility principle I mentioned yesterday, where there have to be decisions been made. Okay, make a decision what actually is the way how you display the data. Make that decision and then represent that, implement this decision, give the responsibility for implementing that decision to a structure in your code. And what can that structure now be? You know it. You have to implement it using logic, because only logic is creating the behavior. You have to pack up the logic in a function or a couple of functions. Okay, at least one function has to represent this whole responsibility. And then, next level, pack up the functions all related to that decision, to that responsibility in a module, or in a hierarchy of modules, or interrelated modules. Okay, so separation of concerns was the first, well, one of the first principles, and I try to like color it here. There's a reader class, right? So reading from a file and parsing the content is one concern I identified. Then display, or no, creating the data to be displayed as a histogram. That's domain logic. Well, that's a concern. Do I get the domain logic right? Calculating the histogram data from the individual cycle times. And then there's a concern of presentation. How do I display the whole thing? So 3 concerns I identified in this simple scenario. And those I now represent as boxes. Finally, boxes. What are missing? The lines, they'll come soon. So we start our architectural journey with boxes. Boxes represent concerns. That's how it all started. And here you see, for this particular scenario, is the histogram concern, some domain logic. This is the reader concern. Well, we have to get the data from somewhere. And the presenter concern, we have to display the results somewhere. That's obvious, right? I think it's pretty obvious. And now comes the next step. We connect those concerns. None of the concerns by itself solves the problem. I mean, that's not the whole program. That's not the whole behavior. But we have to connect those concerns. They play together. They need to be coordinated. And that's what the lines are about. And I'm using, look very closely, I'm using this specific line with a dot at the end. Very important, the dot, not the notorious arrow. You'll see arrows later. But the dot to me means, and to you today in this session, means actually uses, calls. The presenter concern calls the histogram concern, calls a function or two, and the histogram concern calls at runtime some functions from the CSV reader concern. That's all that it means, okay? A needs B, uses B, calls B. That's what this line expresses, okay? Boxes and lines diagram. You're very familiar with that, I'm sure. You do that all the time, like a class diagram, UML class diagram, yes, except for you are using arrows and I'm not using the arrow here yet. Arrows will come later. But I find it very important to discriminate between arrows and those dots. The dot, for me, signifies like hanging on to. I have to grab on. The presenter has to grab on histogram, because without the histogram, it's nothing. It can't do its job. It's dependent on the histogram. Okay. So modules bundle functions, great, and hide details. Hide some functions, so they provide interfaces, differentiating between secret stuff, hidden stuff, private stuff, and public stuff. That's introduced with modules. That's not what functions do. Functions hide everything even though you could say they have an interface. No, that's the signature of the function, but they hide everything, all the logic inside. But modules do that selectively. Plus modules use functions in other modules. That's perfectly fine, right? Sure. Good. That's dependencies. Dependencies, very important term. And the question now is, after setting up this separation of concerns thing with the modules, which modules should your software be made of? How do you answer that question? And Priya says, well, there are best practices. You don't have to reinvent the structure, the structuring of the software again and again. Don't have to invent the wheel again and again. There are best practices. All software, or most of the software, should be separated in these kind of modules, A, B, C. And that's where we start in the 70s. MVC is the first attempt to set up like a canonical idea of this is how you structure at least certain software. You put stuff into a view module, you put other stuff into a model module, you separate both concerns, and you also have a controller module. And that's how you should do it. You should do it, and you should do it, and you should, and everybody should do it like that. And so this is, well, then a common pattern. I look at the next software code base and the next code base, and I can expect it to look kind of the same, because in every one there is the model concern, the view concern, the controller concern. Well, that was regarding the stuff that was written in the 70s, and it was a great idea back at Palo Alto Research Center maybe, and in the context of the Smalltalk language, which was an attempt to implement object orientation. So in that context, MVC came up, and it's even alive and kicking today. You remember controllers from like REST controllers? Yeah, they are kind of like that. Yes. Okay, so it has survived. Good. So, but the question is, or was, quite soon, okay, 20 years later, is that all? Should we just stick with MVC, or can we evolve? And then came, in the 1990s, the pattern revolution, design pattern revolution, and some other ideas in conjunction with object-oriented languages like C++ and Delphi, and later on Java, came up and, well, formed architecture from layers where this is going like around in circles, right? And this is going just from top to bottom. But I call it all SOC architectures because it was just about the concerns to be identified. Here I'm zooming in on the relationships. See how they go in circles. Okay, that's one thing you can do. And see how the relationships become different and simpler in the layered architecture, and that was the point. Make the relationships simpler, because the dependencies, well, they define how easy it is to test the whole stuff and reuse the stuff. And that was the idea behind the layered architecture. And notorious is the presentation layer, show things and get input. Business layer, do calculations, implement your business rules, and then, well, store the stuff in a file in a database. Yes, in the database, a very important and expensive database like Oracle, yes, or SQL Server, or whatever IBM had to offer maybe. So this was essentially, next level was the N-tier architecture. What drove the layered architecture also to separate technologies and to separate out and make this clearly visible here where the money was. And later on the money was here with application servers, but first it was here in the database layer. Okay, so that was the first step. It was a prescription for concerns which concerns there should be identified in your software and package the logic into functions and into modules regarding the concerns, plus the prescription about how those concerns should relate to each other. That's the basic architectural pattern. And everything could have been fine, but people were not content. Wait, look at this. Here is the histogram again, and the histogram is used by the presenter. See here, there is, well, this hybrid. There's logic in the presenter here, and there's a call to the histogram. That's not looking good. That's a functional dependency. And those architectural patterns didn't make a single statement about whether this was good or bad. They just said, this is how things are. You have logic here in one concern, and the logic, well, is interspersed with some calls to other concerns, so just do it. Call the other concern contains logic, well, the business logic here. Now you know what the term logic means in business or domain logic. So it contains some logic here, and also calls some other concern, which mixes in this function logic and a call to, well, another part of the same concern where there's just logic. So this is the bottom of the call hierarchy. This is in IOSP terms an operation, and this is something evil, and this is something evil, and this is something evil too, because it's just a mixture of logic and calls to other concerns or other functions. But, well, the first architectural patterns didn't care. Functional dependencies are bad, really bad, yes, and they abound in these architectural patterns. Logic is still hard to test. Look at this red part here. It's hard to test when it's calling something else. And, well, also this mixture between logic and calls to other functions is hard to understand because it violates yet another principle, which is called the single level of abstraction principle. Stick to a single level of abstraction, and this is low abstraction, this is higher abstraction. Low abstraction, higher abstraction. It's not gonna cut it, no, sorry. Okay, so along came an improvement. The first architectures were content with, separating into different concerns and connecting those concerns in a defined manner, great, but people realized this is hard to test and still hard to understand. What can we do about it? And so there was an improvement. And the improvement started maybe in the late 90s and then got very prominent in the mid-2000s with the hexagonal architecture. This is where the dependencies, as you will see, are cross-cutting from outer to inside, from top to bottom. And here you will see they turn around. Here they are concentric. That's the concentric architectural models. This is the cross-cutting architectural models. Both, however, can be subsumed under the DIP architectural patterns. Okay, so what do we have? The overall generic dependencies, there's just one kind of dependency I showed you before. This one knows the lower layer, the other concern, and calls it. This one knows the other concern and calls it. Well, what else? Well, differentiated dependencies distinguish between a runtime dependency at runtime, when behavior actually is created. This concern calls that concern calls this concern. There's no way around that. But at design time, well, there's a different dependency, which incidentally right now points in the same direction. Okay, but there are two kinds of dependencies. Runtime call dependency, design time knowledge dependency. Do I know about this other concern? Do I know about the implementation or not? Okay, and this is where the DIP entered. Once these dependencies were differentiated, we could start thinking about well, does that need to be direct? And the answer is no. I think it was Robert C. Martin who wrote first about the dependency inversion principle in somewhat 1995, 1996. And what he said was, well, yes, at runtime, this one depends on that one and that one on this one. Yes, but at design time, there doesn't need to be a straight dependency between the two concerns, but rather than that, there should be a dependency just on an abstraction of this concern. And in the end, an abstraction is not the implementation. An abstraction can be an abstract base class, can be an interface. Okay, so as long as we just know the interface, to make it concrete, we just know an abstraction, the interface, there can be a multitude of implementations. We don't need to bind ourselves up here to a concrete implementation, but just to an abstraction. And at runtime, this abstraction will be instantiated with something concrete, and then we call at runtime the concrete implementation for the abstraction. So this is referencing an abstraction, and this is implementing an abstraction. And because this is different from calling an implementation, I needed to differentiate the lines. This one is the typical reference or knowledge line with an arrow at the end. This is the typical implementation line with an open arrowhead at the end, like implement a base class. And this is, well, kind of my invention, just the call relationship. Okay? So now we have the DIP, dependency inversion principle. Don't depend on concrete stuff, depend on the abstract stuff. Great, okay. Well, what's not to like about that, right? Still though, we have to see at runtime there's no difference, right? At runtime there's no difference, and because there's no difference at runtime, there is still hard to test logic up here. Because the logic up here is calling the logic down there. And let me maybe ask at this minute, right away. So why in the first place should a business layer call persistence logic? Just tell me, why? Why should business logic call persistence logic? I don't have a clue. I never had a clue. Why should business logic call persistence logic? Yes, business logic needs data to work on, no doubt. But why should it get the data itself? Why should it be concerned about where this data comes from? What does that have to do with business logic? I don't know. And we'll see other people either didn't know, and they tried to do something about it, but they actually didn't succeed, I would say. Still, from top to bottom, the cross-cutting dependencies are running. And here's what it looked like before DIP. There was the histogram. The histogram calls at runtime something from the persistence or CSV reader concern, and it knows the CSV reader implementation before DIP. And after DIP, there is the histogram calls the CSV reader, but it knows only the CSV reader abstraction, and it gets from the presenter a call to run, and the presenter knows the CSV reader implementation and passes that on to the histogram. So that's dependency injection, right? At runtime, dependencies, concrete implementations get injected into the logic which actually needs them later on. That's production time, and because it's like that, because we differentiated now the abstraction from the implementation, we can implement it alternatively with a surrogate at runtime, at test time, which is a runtime too. Here for this test, there's a different implementation of the CSV reader, and the histogram actually calls this surrogate, so we can focus our test on the histogram logic and know nothing from the real CSV reader is distorting our results. Okay, great, testing got improved. Yeah, we can create more pinpoint tests. That's good. Okay. Indeed, DIP increases testability, and it's no small wonder. The DIP architectures got invented after 2000, after the first automatic test frameworks came along, like JUnit. That happened 1999, 2001. That was a time for TDD, XP. TDD got invented, and so we were very focused on testing. Great. And that had to be made easier. Great. And that's where the DIP architectures helped. But this was made easier, but it adds complexity, right? There needs to be an abstraction for the implementation. That's more complexity. We have to inject instead of just create where it's needed. That's more complexity. Okay, but maybe it's worth paying the price. I don't know. This is again this is a test here, and the test is there's an ICSV reader mock implementation that gets created in the test, and then the histogram is called with the mock reader, and so on. Yeah, he's not looking very happy here, for a good reason. This is DIP, and it didn't change, even though something changed on the next level, 2005, when the hexagonal architecture got invented. So what were people not satisfied with? Design time dependencies, following the dependency inversion principle, going from top to bottom here. And you see the top is depending on an abstraction. The abstraction is on the same level as the implementation, but it's depending on this at design time, depending on this on runtime. Okay, this sounds good. What then did the hexagonal architecture and then the clean architecture, the concentric architectures do differently? They moved, and that's only the only thing they did. They moved who was responsible for defining the abstractions. That's all. Here, the implementer is responsible for defining the abstraction. The implementer of the abstraction business layer is, well, the business layer, and here it's for persistence layer. And here you see how this changes. The persistence abstraction gets defined here, right in the middle, by the user, who uses a concern, defines how the concern is supposed to look like. That sounds like capitalism, right? The market-driven production. The user, the buyer, defines how the service is going to look. And that's what's happening here. And who is the ultimate, most important concern? It's the one in the middle. It's the domain. The domain is supposed to overrule anything else, all else that is just peripheral. That is what the hexagonal architecture does. It puts the weight into the middle and says, domain first, periphery second. And because domain first, it's the responsibility of the domain to define the interfaces of all the other concerns. Right here in the middle, that's where the definition sits. And now you see how the dependencies change. Look, the top dependency here, the adapter or the presenter or whatever, the user interface concern, points to the middle because it needs to know the abstraction of the middle. And then the adapter for the persistence for the data access points to the middle because it needs to implement, not just use and know, but implement the abstraction the middle is giving for persistence. And so this one is pointing down, this one is pointing up, even though it's different arrows. This is the knowledge arrow, this is the implementation arrow. But what doesn't change, you see it? What doesn't change is the red lines. It's still flowing from top here to bottom there. Nothing changes. Okay, so This is, for me, the generic concentric architecture. We have a periphery where the environment is connected, interaction with the environment. Sometimes the environment triggers work in the software. Sometimes the software triggers the environment because it needs a resource. And we have the red lines going from periphery to core to periphery again and out to the resource. But we have those, the blue lines here, purple lines, they go inside, they point from the periphery to the center. Concentric architecture. And that's the architecture. This one, the hexagonal one, or ports and adapters and clean architecture. Flow of control is unchanged, the dotted lines, but the knowledge and implementation arrows point to the center. That's all. Does that change anything for testability? No. It's not getting better, and it's getting worse. So concentric architectures change ownership of abstraction, the abstraction from the bottom, but moved up to the middle. Remain DIP architectures, nothing changes, so need to have the abstractions separated from the implementations, and somebody has to inject something. This mess of logic and calling other functions and logic again and other function calls and so on, this mess stays in place. And even the inventor of the clean architecture, Robert C. Martin, says in his book, well, after he presented this as a clean architecture, okay, very clean, very orderly, right? You like your child's room to look like this, very orderly. Lots of stuff in there. And he says, well, much of the complexity, so he says there is complexity, was used to let the dependencies point in the correct direction. That's all. So he's putting in complexity to get this pointing inwards. That's all. He's adding complexity to just turn around, in fact, one arrow, this one here. What the FF? I don't get it. But people are obsessed with that. That's the latest craze, still, 2025, after 12 years. I don't get it. Yes, Arjun, rightly so, asks, is that complexity really necessary? And Priya answers, well, not necessarily, because, and this is why I depicted her in front of an orchestra, well, how about separating something out even more and orchestrate stuff? And those who attended my talk yesterday already know what's coming. There's another principle. Okay, that was invented in 2013, the IOSP principle, and that launched, not really 100% true, but with this principle I can classify 3 architectures as going beyond the clean architecture. Maybe they are the cleanest architectures ever, who knows? Okay, before IOSP, I have to make that clear very quickly, can't delve into it like yesterday. You see there's a function here, it's called F, and it contains logic, the infamous brainfuck logic, right? Calls another function over here, which only contains brainfuck logic, then continues with the result with its own logic, calls another function over here, H, which contains logic, and call to yet another function and some more logic, and then finally continues down here with this logic, right? This is your code base, in essence. This is how your code looks, all over the place. Some logic, calling another function, more logic of your own in the same function, calling another function, more logic. This is how your code base looks. And this is hard to understand because you are still allow yourself to mix those logic parts with the function calling parts. That's why there's no bound to growing your functions. 100 lines, that's just great. 500 lines, great. 1,000 lines, great. Okay, we have to constrain that before the IOSP. This is a functional dependency where there's logic and then calling another function and there's logic again. Functional dependency, hard to test. How do you test this? How do you test just this logic? How do you do that? You can't. How do you do? Well, you can't without the DIP. So you need the bloody DIP to be able to test just this. But you can't even test just this. You always have to test this and this and this in conjunction when you replace this with surrogates. Oh, it's even tiring me now what I'm speaking about. Okay, requires DIP for targeted testing, and even then it's not really targeted because you do not get disentangled those two parts of logic. It's the same program, the same logic, but structured in a different way, now according to the IOSP. And look how simple this is. It's all the logic contained in functions, which can easily be tested. They are called operations because they only contain logic. That's a question? No? Okay. So all logic that was present here and scattered about and distributed across different functions now gets put into functions of its own. And this is coordinated, orchestrated, integrated, composed on different levels. And look at how easy those levels look. They are just calling functions. Nothing more, nothing less. No more logic in there. This is easy to understand. You understand 3 lines of code calling functions, right? This is really easy to understand. You understand this, you understand this. You understand the brain fuck? No, that's fine. You don't need to understand brain fuck. You just need to test it. Test it with an expectation for what K is supposed to do, or H1 or F2.1, whatever. You have an expectation from the function name and just throw a couple of tests on it, at it. That's great. That's what you do here. Okay, this is the IOSP, Integration Operation Segregation Principle. It lets look your code like this, very clearly distinguishing functions which contain just logic and functions which don't contain any logic but just compose their behavior from other functions. Okay, keeping that in mind, again, easy testability. If you want to test this, well, you can, but sometimes you don't even need to. And if you test this, you never replace this. No, never is wrong. You mostly don't replace this with surrogates. So what is absent here is the DIP. No added complexity with abstractions. Not needed. Not needed. Sometimes you do it, nevertheless, but it's not needed. It's not at the core of the architectural pattern we are getting at. So no DIP required for targeted testing because there's no more dependency here. Okay, IOSP makes logic easy to test because it's isolated in functions without any dependencies. And the integrations here, they are trivial. And the IOSP increases understandability because this is easy to read from top to bottom, just a couple of function calls. This is bound to be very short, 10 lines of code, not more, 12 maybe. This is easy to read because it's just a couple of lines, maybe 20, 30. Beyond that, you want to refactor it and let it become an integration. So this is small functions without a very specific bound. You don't have to say, my functions are no longer than 15 lines. No, not necessary. You feel that. A developer feels when this is still okay, maybe 25 lines in one case, maybe 35 in another case, maybe just 5 in yet another case. You feel when it's enough or too much. And you can test it easily without any dependency injection. Okay, and IOSP decreases complexity because, well, we don't have to worry about any additional abstractions. And it creates abstractions itself because these are functional abstractions. They are kind of defining your own language. That's what you do. you build languages from lower levels onto higher levels, and the low-level vocabulary are operations, and operations get composed into higher-level vocabulary, which gets composed into yet higher-level vocabulary. Abels and Sussman termed that in the 1980s stratified design. Build your software from layers of languages. And even Alan Kay in a, I don't know, 2000 lecture, somewhere around maybe 2010, a lecture in Berlin he spoke about that. That's what he meant when he invented object orientation. Yes, build your software from layers of languages, called strata. This is the first IOSP architecture. I call it Yoda architecture. Well, yes, you know why Yoda, to remind you of the Yoda guy with his superpowers, right? But it's written with an I, and you'll see in a minute why it is an I. It's, as you would imagine, a concentric architecture because the domain logic is put at the center. Yeah, that's where it belongs. Great. And there's still the periphery, but the periphery I clearly separate into the periphery which gets triggered from the outside and which is triggering the outside. The hexagonal architecture doesn't do that so strictly, but I find it very important. Is control flowing in or is control flowing out? Okay. The portal here is where control flows in from the user, and the provider down here is where control flows out and is controlling some resource. Resources can be databases, of course, file systems, yes. Can be other software, can be the time, and can be random numbers. Wherever hardware comes into play, that's a resource and needs to be encapsulated. That's a concern you have to be concerned about. And of course, the core domain at the center, yes. But one more concern, and this is a novelty here with the Yoda architecture. There's one more new concern which hasn't been seen, hasn't been extracted in any other pattern, and that's the integrational concern. Integration is a concern in and of itself. So the colors stay the same. I'm pulling out the integration right here in the middle. It's like the connecting tissue in your body. This connecting tissue, it's almost looking yellow in your body, well, sorry, is putting together all the other concerns. See, it's depending on them. Yes, technically it's calling them, but it doesn't do anything with the results. So it's not really bad. Here, there is, you see again, brainfuck logic. Here is where the logic sits. And how do they work together? How can they be integrated up here, pulled together? That's through data, right? These two concerns share some data. These two concerns share some data, great data structures. So the operations are ready to collaborate with each other without knowing each other. Because the knowledge, this is not calling that one is not calling this one, like in all the other architectures before it. It's just the integrational layer which knows about all of them and puts them together in a functional manner on a higher level of abstraction. And some of those concerns have to call to the outside, right? Some APIs, and that's the portals, the communication with the users, and the providers, the communication with some resources, some databases, whatnot. And that's where the Yoda comes from. Integration on top. Integration integrates, composes functionality from operations. Then data is used to, well, so they can exchange information. And APIs are at the bottom. That's what some of the operations are based on. That's the Yoda architecture. And the point about the Yoda architecture is to identify integration as an integrational part of architecture. Go on. What happens? What's the purpose of this? What do these dependencies mean? they allow the integration to set up a workflow like a manager. No, better to say like a coordinator. I'm coordinating you, you, and you in a workflow, so you work together and I can go on a vacation. Because I set up your communication. I set up what you do together, and that's all I need to do. I don't need to check on your results all the time. I just need to put together the right building blocks in a certain process, so those building blocks can work together without actually knowing each other, because that's part of the process, taking results from here and passing them on to here, so this part can work on the results of the previous part. But a part further downstream doesn't know what's happening upstream, and an upstream part doesn't know what's happening downstream. And that is absolutely contrary to everything else in architectural patterns. Here you don't see business logic, core logic, calling, even knowing about data access. Data access is happening here. Yes, it's reading data maybe from a database, and this data gets passed on to into the domain logic, but the domain logic doesn't care where it's coming from. That's the responsibility of the integration, to pull together all the different parts into a larger whole for the behavior. Okay, integration creates data flows. So the Yoda architecture does not need DIP, gone. All the complexity of DIP is gone, gone, because you distribute logic in a different manner. And, well, thus it reduces complexity. As you saw, all the logic was pushed down or pushed right to the bottom of a call hierarchy. That I find much easier to understand, less complex to analyze than those hybrid methods of some indeterminate length, which you cannot really read after 20, 30 lines. Leads to true abstractions. So coming back, you remember the layered architecture? Layered architecture was presentation layer, business logic layer. And so what this is suggesting is that a higher level, a higher layer is more abstract, right? Yes, business logic is more abstract, right, than data access logic. Yes, right? Yes. Okay, you all fell into the trap. It's not true. Why is business more abstract than data access? Is business doing the same as data access, only in a more abstract way? No, it's something completely different. Business logic is doing something very different from presentation logic. It's very different from data access. It's different, not the same, more abstract, not the same with less detail. Not true. So it was always a wrong suggestion, an illusion that a presentation layer would be more abstract than a business layer, would be more abstract than a data access layer. Not true, never was true. And this is not true in the clean architecture, which is suggesting the core is more abstract than the outside. Not true. What is true is that this is all on the same level of abstraction. Data access, same level of abstraction than domain logic and than presentation logic. It's the same level of abstraction. It's just different, very different concerns. And to raise the level of abstraction is to wrap something around them and pulling them together, composing something more abstract out of them. So this, for the first time, really creates layers of abstraction or stratified design. Okay, here is an evolution. We have only 15 minutes, but we're getting close. Thanks. Evolution, this is Yoda, the essence of Yoda. Integration extracted from those operational concerns, I would say. And now I'm differentiating even more. I'm differentiating, I'm pulling out part of the integration. So I'm first, on the first level, I could say, or stratum, I'm integrating just the presentation and another integration. And this integration, the processor is integrating the domain and the data access. Why do I do that? What's the purpose of that? Why two levels of integration? Well, this flow between the user interface and the processor becomes easier to understand. It's just 3 steps. And this flow is also very easy to understand. Inside of the processor, it's between the data access and the core. Okay, but there's more to it. Because if I continue the differentiation, I find that user interfaces usually are consist of 2 different parts. One is collecting data from the user. That can be a form, you can enter a prompt, whatever, or point at something. And then it's projecting results from created by, well, something internally, projecting results, maybe as a graph, maybe as some text, maybe filling out a form, whatever. So that's 2 different responsibilities of all user interfaces, collecting data and projecting data. So why not pull them apart into 2 different sub-concerns of the user interface? That's what I'm doing here, collection and projection. Now we see the flow already, right? You're getting used to this. Collection, processing, projection. That's the flow, always. Collection, processing, projection. And now I'm asking you, what of those concerns, which of those concerns are easy to test and which are hard to test? Well, this one is easiest to test. Well, it hasn't any dependencies, really no dependencies at all. It's all in memory. This can be pure functions. You don't even need classes. You don't even need object orientation. It can be pure function, and this then is called, to differentiate this from the other part, is the functional core imperative shell pattern. Functional core means it's just pure functions, static classes with static functions, input, output, no data access, nothing. Great. That's the easiest to test. Then comes this. Yeah, there's a resource dependency. Maybe this accesses a file or a database, but still, taken just by itself is quite easy to test. Okay, somewhat more effort, but still. Okay. And then to test this here, both integrated together, it's still okay. I wouldn't in all cases replace this with a surrogate. Wouldn't necessarily introduce DIP here. I would go with testing a processor, setting up an integration test up here, testing it with the real resource access and the real domain logic, because what I don't want to test is whether this is correct and that is correct. No, that's not the purpose of an integration test. The purpose of an integration test is to test if the integration works, if it's integrated in the right manner. Okay? So what's hard to test? All kinds user interface. User interface dependencies, you don't want to do that. You can go there, there's technology. For a couple of decades, there's been technology to test user interface code, but it's really not fun, really. So the purpose behind this is to separate out everything user interface from everything non-user interface. Everything hard to test from everything comparatively easy to test. That to me is on top of Yoda architecture, another architectural pattern, which I call the Sleepy Hollow architecture. You know that movie? Yeah, it's a fun movie. Johnny Depp and Christina Ricci. So this is the head. The head integrates those 2 parts of the user interface concern with the processor, the head. But the head in that movie plays a negligible role. It's not very important. Important is the body and the horse without the head. That's wreaking havoc on a village. So this is the main part, the body. You separate that out and hide these operational concerns behind this processor integration. And that's where you can put acceptance tests. Very broad, very high level integrational tests, which do not prove correctness in all cases, but which prove this stuff is actually working together. Okay, Sleepy Hollow architecture. Yay, Arjun is happy, great. This is a more concrete example. So we have the application here, the UI, don't differentiate that. Processor domain persistence, okay. I differentiate the UI into the collection and projection part. Domain persistence still the same. This stays the same. Now this down here, remember the scenario is differentiated into a couple of classes. Histogram still is the domain logic. The CSV parser is kind of just a data structure, an active data structure, where it takes CSV textual data that is provided by the CSV reader and structures it into a data structure. And that is the issue. Both share the issue as a data structure. This one produces issues and this one consumes issues to build the histogram from that. And the CSV reader is just providing a plain string or whatnot to the CSV parser. And when I'm saying provides to the CSV parser, none of those knows about the other, right? It's the processor who knows this one gets data from a file. And this one knows where this data goes here and knows where the issues go here and where the issues, whatever that produces the histogram goes, well, it flows up. And this one knows where to put the result from the processor to projection. So that's a differentiation here. As code is hard to read in the back, I guess, but it's the same as you can see. That's what I want to point out. This is integration, straightforward, creating classes, calling function those classes. Easy to read. There's logic, UI collection. There's logic, UI projection. Okay, here's the processor. Let's go down to the processor. And you see the processor, two function calls. One of those function calls, two function calls, so it's a two-level integration in the processor. And what's getting integrated here is logic in the histogram, logic in the parser, logic in the reader. It's all just, so to speak, brainfuck down here, and this is function calls, nothing more. And there's an issue data structure, very easy. Okay. What does it allow? It allows for easy acceptance tests on the processor, and the acceptance tests are nothing more than, well, alternative heads. One desktop application head, one REST API head, and all this stays right the same. Okay, Sleepy Hollow increases flexibility. Well, you can exchange the heads and increases testability because we extract this for acceptance test, by the way, which can be and should be negotiated with product owners. And you shouldn't even start programming as long as you don't have a clue about the interface of this concern here, of this module. And once you have the interface of this one here, you have to prod the product owner and tell him, okay, we have to get so specific that I can set up an acceptance test. And as long as that doesn't happen, you don't start coding. That's like your triage point. You know what a triage is? Okay, it has to do something with death and battlefields and stuff. So, but the point is about the triage to save your resources. They are really scarce. And you want to focus your resources on where requirements are clear enough. And this interface of the processor gives you the criteria for when is it clear enough. When you have the processor interface, you know exactly what it's publishing in terms of function, and you have test cases for exactly those functions. And not earlier are you going to invest resources into programming down here. Don't. Okay, so let's step back a little bit. All those architectural patterns. ran in 2 dimensions. We talked about, well, first the concerns. They had different ideas what to separate out into concerns, what logic to pack together. And it's too long already? Damn it, okay. And okay, so you have to read up my presentation and talk to me on LinkedIn maybe. And the other dimension was dependencies, and there's in fact a 3rd dimension, that's scope. That's what I wanted to talk about next with you, but my time's up, right? 5 more minutes? Okay. Okay, no question, there's no questions. No more input is needed. And that's what the next frontier is. The next frontier is scope. We have done all we could down here, but we need to focus the scope, but because, well, even the Sleepy Hollow architecture, what to focus it on. And I'm saying we should follow the idea of the vertical slice architecture, which says, well, don't implement a whole architecture for all of the requirements, but focus on a slice of requirements. We can talk at length about how to get to those slices, but pick out some requirements which cut through all those layers, all those concerns, which essentially work together, cooperate together, cut through that and do an architecture only for that. And I'm putting this last for 2 reasons. One is it perfectly well can be built on top of the Sleepy Hollow architecture. See, there's one application interactor up here, the head, great. It's representing all of the scope with all the user interface, all the buttons and whatever you need. And then behind the scenes, it's splitting up the actual creation of behavior in different slices with its own processors and own operational concerns, own processors, and so on. And here you can see the full scope is separated into parts. And those parts can be implemented separately. That gives you flexibility in distribution of work, in order of work, and so on. So these are increments with their own architecture. This is a new thought. Increments, agile thinking, right? And each increment gets its own architecture. Wow. Okay, there's a problem to be solved. We'll see that in a minute. And that's the problem of the single model. All those increments in the end, of course, are working on the same data, right? Yeah, right. That's why we always had to have, even before slices, had to have the single model. The single big model in our database, the single big model, object model in memory. That was so important. It was always so hard to get right, and it was never stable. And one of the symptoms of this, its instability is, well, optimizations in databases with views and denormalization of relational databases. Because the single model, the single normalized relational database model never cut it for all use cases, and use cases are the things represented by slices, you could say. So we have to give up to become even more flexible in terms of architecture, this single model here, and instead, well, follow the people on LinkedIn who are promoting event sourcing. So instead of pushing data into a single model, be that in memory and or in a database, instead of that, record changes to state in an event stream. This is going very fast right now, very fast. But it's a thing. You can look it up, event sourcing, event modeling. It's not event-driven programming. No, it's event sourcing and event modeling. Push little changes down into this infinite append-only event stream, and then, horribly dictu, create a multitude of small models for each of those slices in memory on demand. That's crazy. That's against everything you learned the past 20 years. But it's a thing, and it's working wonders. because it's decoupling. Decoupling is always a good thing, right? It's decoupling increments from each other. They don't have to agree on a single model, but only on events, and each slice picks from the menu of events what it likes to keep its own local models updated. And you put a next slice next to it, you don't have to care what other people have set up in terms of models. You just do your own model. And that model of data can be a single number, or it can be a huge conglomerate of objects. You decide. And this is adding another layer of flexibility to architectures, because it takes out the pressure from the domain model, which is still at the center of the clean architecture. Okay, very fast, sorry. Event sourcing, decoupled slices. Yes, slices can be structured according to the Sleepy Hollow architecture. Event sourcing increases flexibility through several models, a multitude of models, and productivity, because we can work on all those slices in parallel. You can scale it with people. Actually, throwing people at a software project, even if it's late, if they work on their own slices, doesn't make it later, like Frederick Brooks said, but can increase productivity, makes it to be released sooner. So, initial questions, is there anything more? Yes, there is more. Developments happened after 2012, and there is more architectural patterns that can be found. Yes, thank you very much. Sorry, 15 minutes, damn it. Question, yes?
Yeah. Thank you so much for this amazing session after yesterday's groundbreaking session. I had one question from cybersecurity standpoint. While going from DIP to IOSP, it reduced the complexity.
When going from?
DIP to IOSP, architectural pattern, it reduced the complexity. But from cybersecurity standpoint, if complexity is reduced, then someone can inject the malware easily. I mean, he could understand that code pretty much faster, right? If complexity is reduced. So what is your thought on that specific thing? Because if complexity is reduced, then it on the other side, it makes easy as well.
So
right?
you're saying we should increase complexity to build more secure systems?
Absolutely not saying that. Just would like to know your thought from that standpoint, like kind of a...
That's completely orthogonal to each other. I want to reduce complexity of my code.
Correct.
And I have to deal with security attacks, well, through some code maybe, which should have little complexity.
Correct.
Or make it otherwise in somebody who's evil, incapable of attacking it. I don't know. So it's orthogonal. No, I want to reduce complexity. Go away with your security concern. Don't. It's a functional requirement, or maybe it's a non-functional requirement, and then security is a concern. Put security in your design. Make it secure by design. And if you're talking about a secure system, so fun aside, right? You're talking about secure system, show me your architecture where you can point and say, see, this is where security manifests. Show me the concern. I don't know how you manifest that, but show it to me. Maybe there's an encryption module. Maybe there's some, I don't know, whatever module. Show it to me in the overall structure. And this overall structure still, of course, should be less complex than before. Okay.
Here, but yeah, he'll be around and you can ask any questions. And yeah, wonderful audience, thank you. And it was really insightful talk. Thank you, sir. A round of applause for the speaker.